This video is on going from 2D cyclohexanes to 3D conformations. So the question is, how do we equate a flat six-membered ring to a chair structure? Well, it's relatively easy to associate when there's nothing else on the ring. We have a six-membered ring and we have a weirdly drawn six-membered ring. But once we start putting substituents on it, we'll notice that we're using wedges and dashes. Now it turns out that the wedges do not automatically mean that they are axial, and the dashes do not mean that things are equatorial. It's slightly more complicated. They are relative positions. So if we had all positions wedged on a 2D cyclohexane, the chair would look something like this. Notice how all the substituents are pointing up, relatively speaking. Whilst if everything was dashed, all the substituents are pointing down. So there is a correlation between wedged and dashed and up and down. Okay? Make sure to understand this correlation and practice drawing it. Okay? So next is the question, which one is better, axial or equatorial? Well, it turns out equatorial positions are favored due to the axial positions on the same face interacting with each other. For example, we have this methyl cyclohexane. If we draw the equatorial methyl cyclohexane, no big deal. The methyl group is staggered. It's going to be at its lowest energy conformation at this point. However, if we draw it axial, yes, it's still staggered, but we notice that this methyl group is starting to occupy the space of the other axial positions, hydrogens in this case. This is what we refer to as the diaxial interaction, or more specifically in this case, the 1,3 diaxial interaction. Of course, if this is the case, the bulkier the group, the more strain there is going to be, and therefore the more likely the conformation is going to have the bulky group on the equatorial position. Single atoms or linear species occupy the least space, whilst branched or longer chain groups occupy the most space. Given that ring flips occur naturally, it means that there will be a mixture of both axial and equatorial species present. However, the lower energy species is going to be favored, and the higher the strain, the less there is going to be of the high strain species. Correct? Makes sense? So therefore, when we're discussing which one is favored, we're usually just talking about which one there is more of. Okay? So here's the question. Which one of these two species will have more of the axial conformation? You may pause now. And here's the answer. Of course, it wouldn't be organic chemistry if it was easy, so exceptions do exist. For example, if the axial atom interacts positively with other atoms axially, then it's going to be favored. What kind of interaction would this be? For example, can it form a hydrogen bond? Or maybe a charge interaction, i.e. let's look at this bromine over here. Its large electrical cloud will probably interact with the partial positive charge of the hydrogen. Therefore, you get a positive electronic interaction. As stated, this is an exception though, so just look out for it in a question where you are being asked directly why something is as it is.